Well, welcome to Chapter 3, Basic Data Structures. Here we're going to about linear structures. The whole chapter is about linear structures. We're going to cover stacks, queues, dequeues, and list, and we're going to see examples of each of them in use. While we're doing this, we'll learn more about our abstract data types, which are more examples of classes. So you should become more familiar with classes by the end of this. So first, a linear structure. We want to store a bunch of references to objects or a bunch of numbers or a bunch of strings, and there's a lot of ways of storing that in memory. We're going to learn through this book. You can use trees and graphs and all kinds of different structures, but there's one general category of structure called a linear structure. Here's a little picture of it. You'll notice that it's a bunch of things in a row, and so basically you can add items to a linear structure in different ways, but once you add them, they retain the relation to the neighbors that doesn't change. So if I add something in between these two, between B and M, it'll have a relationship that B will come before it and M will come after it. So linear structures always have that relationship. What difference between the different types is where and when you can remove items. So in other words, once an item is added, it stays in that position relative to the other items that came before it and came after it. I like to think of a line of cars and a line that follow rules that once in the line they cannot pass another car to change places, and when they can leave and join the line depends on the rules of a particular data structure. The first data structure of this type we're going to study is called a stack, and they always give you a stack of plates as an example. So when you stack plates, you always have to first put the first plate in, and this is called the base. Then you put the next plate in. It always goes on top of the stack that's already there, so you can only put plates on top. And then if you want to get to a plate here without unbalancing the stack, you have to remove all the plates starting at the top to take each one off until you get to the one you want. So this is the essence of a stack. Here's a picture of it. So a lot of times we'll think of stack as vertical, where this is the base. And these are the operations that a stack has. We're going to learn that these operations form the method or the interface for the abstract data type for stack. So however we implement a stack, they'll always have these 6 operations. So the first operation is just to create a new stack. So that's creating an object of type stack. So we just say stack parentheses parentheses. It returns a reference. We can store it in a variable. You can get the size of the stack by once you have that variable dot size. You can push an item on the stack. So you say the name of the stack dot push, and you give it an item in parentheses, and it puts it onto the top of the stack. You can say pop an item from the stack. That removes the top item of the stack. So this item would be removed from the stack, and it would be returned by pop. So you could do something with it. There's also a peek, which allows you to get a reference to what's on the top of the stack to look at it, but it doesn't remove it from the top. And then finally there's isEmpty, which will test if the stack has 0 items. So it returns true if it's empty. Here's an example of a Python stack. So you have the base, you have the stack. Python stacks, you can have mixed data types. So I have a number, a string, a boolean, and a float all on this stack. One of the major features of stacks is called that they're last in, first out. So if I'm putting things on the stack, I put in 4 first, and then I put in dog, and you see as I stack them, they're like the plates going on top of each other. Then I put in true, and last I put in 8.4. Now when I remove them, the last in, which is the 8.4, is the first one out. That's what LIFO or LIFO means. So this is a LIFO structure, which is always associated with a stack. And so the first thing I pull out would be the 8.4, and the next thing I pull out would be the true, and then dog, and then 4. And you'll notice that the order we put them in, going from 4 to 8.4, when we pull them out, they actually go from 8.4, they go the other way. So they go 8.4 comes out first, then true, then dog, then 4. So this is actually in reversed order. And so one of the things that stacks are very good for is reversing the order of a bunch of items. So if you have a list of items, it'll reverse it all. It's also good for matching up nested structures, and we're going to study a few of those, but one of them would be parentheses. So whenever you have for every pair of things, so every left parentheses, you have a matching right parentheses, and you want rules that they want to be balanced, this will match that up. So here's the actual definition of the methods we're going to define in a stack class. So when you make objects of type stack, they will have exactly these methods. So this is called the stack abstract data type. Abstract data type presents this interface, which is abstract because we don't know how it's going to be implemented. In fact, we're going to see we can implement it in different ways. We're going to show 2 ways, and I'll mention a third. So stack just creates an empty stack and returns a reference, and then you use that reference dot all of these other methods to invoke the method, just like we did in fraction. So push would push a new item on. Pop removes an item and returns it. Peek looks at the item. Is empty returns true or false, and returns true if it's empty. Size returns how many items are on the stack. So here's an example that's in the book. So we create a new stack, so we store that in S. So the stack now contains nothing. Then we say is empty, and it returns a true. Then we push 4 onto the stack, and after we've done that, the stack has a 4 on it. And then we push dog on the stack, and you'll see now it has 2 things on it. Now in this type of reference here, you can see the right-hand side is the top of the stack. We can peek at the stack, so it returns dog, but it doesn't modify the stack. We can push true onto the stack. We can get the size, so that will return 3. We can ask, is it empty? It's not empty, so it returns false. Then we can push float onto the stack, so now the stack has 4 items. We can pop the float, so the stack, the 8.4 goes away, so we're back to 3 items, and it returns 8.4. We can pop another item, so it returns the true, and then you just have 4 on dog. And then finally we can get the size, and it's 2. So this will give you an idea how the stack works. These are using all the operators that we have for a stack. So this week we're going to talk about 2 linear structures, the queue and the deck. So a queue, pronounced like the letter Q, is actually from the English word for to wait in line. So you see a simulation here. Here's the end of the line, which is the rear of the queue. And here's the front of the line, and we have a person being serviced. So if you get in a line, just like a normal line, if you're the first person in line, you get serviced. If you're the last person in line, you have to wait till everyone else is gone and been serviced until you get serviced. So here's what an actual queue structure looks like. We have a linear structure. You put items onto the structure, and that's called enqueuing. And you remove items off the structure, which is called dequeuing. Other books use different terms. They might use remove and insert, just so you know. This side of the queue is known as the back of the queue, similar to the back of a line. So you get in the back of the line, and then you have to wait till you get to the front of the line. There's no way to get in and out of the queue once you're in the line. Unlike a real line, you can just decide to give up and leave. That's not allowed in a queue. So it's not till everyone in front of you, all the items in front of you have been dequeued and taken off, and you are moved to the front of the line that you can be dequeued. A queue has the nomenclature. It's called first in, first out. So the first person in the line is the first person out of the line. So FIFO, F-I-F-O is what this structure is known as, a FIFO structure. The most recently added item in queued has to wait until everything else on the queue is removed from the queue or dequeued before it can be removed. Queues are used in computers a lot. One example is when you type on your key, there's a keyboard buffer. So if the computer is busy doing something, you can continue typing. It won't miss what you've typed. It puts it into this buffer, and the keys are taken out of the buffer in the same order they were put in, which is one of the essences of a queue. The print queue is also used on your computer. So if you've ever had a slow printer, maybe it prints photographs, you can ask it to print jobs, and as the printer is busy on that first job, you can ask it to print the second job, a third job, and so on, and it will queue up all those jobs in a line, and so internally as what's called a print queue. Actually scheduling the processes on your computer many times follows a queue. So there's a queue of things waiting to run, and they're given some time to run, and then they're put back on the queue. So each one's given a little time slot. It's actually more complicated than that, but that's a common way of, a simple way of scheduling processes on a computer. In general, in computing, anytime you're communicating between two entities, they could be two processes on the same computer, they could be two processes on remote computers, and you're passing information, usually those processes are running at different speeds. So a queue is primarily a place to hold information to accommodate the fact that things are working at different speeds. So that's used in a lot of places in communication, especially in when you start working with moving information over a network, you use buffers and queues. So a buffer is basically like a queue in that things come in and they go out in the same order they came in. The ADT we're going to design for queue has this exact list of methods. So it has a constructor, queue, so that's how you create a new queue. So that returns a new object of type queue. We have, once you have an object A, you can enqueue an item, which will add an item to the queue. You can ask that the queue dequeue an item, which will return the item off of the queue and remove it from the queue. You can check if the queue is empty, so it returns a Boolean true if it is empty. And you can call object.size, which will return how many items are on the queue. So here's the example from the book of running a queue with these methods. So it creates a new queue, it checks is it empty, it returns true. It enqueues the number 4. They use a list internally to represent a queue at this point. You can enqueue dog. Now you have two things on the queue. You can see that in the list they're using the left side of the list as the back of the queue. Enqueue true. So now you have true, dog, and 4, and true is at the back of the queue. You can get the size at this point. It returns 3. You can check if is empty. It's going to return false. Now you can enqueue something else. It puts another thing on the queue. And then you can dequeue. It's going to take the first item you put on, which was the 4 up here. So it removes it from the queue. You can dequeue again and it removes dog. And then you can get the size, and there are 2 items left on the queue. So it gives you the basic idea of the operations of the queue. Now queues are useful in computer simulation. We haven't talked about computer simulation, but computer simulation is a simulation run on a single computer or a network of computers to reproduce behavior of a system. A simulation uses an abstract model, which is a computer model or a mathematical or computational model, to simulate the actual system. Simulations are very useful, so we'll talk about that in a little bit. The first simulation is the game of hot potato. You can read about this game in the book. It has kind of a bad origin, but the game of hot potato is you have people in a circle. One person starts out with a potato and passes it to the next person n times. So it's passed around n times to the left. Then the person with the potato that has it has to leave the circle, and before they leave they give it to the person on the left, and then you repeat step 2, so the person now holding the potato has to pass it in people to his left, and then whoever's holding that leaves, and so on. So go ahead and try out the code in the book. It's pretty simple. I'll go ahead and show it to you right here. So you have to again have the Python's library available, so you can drag it into your project here. Notice I have mine dragged in as a folder. You create a brand new queue, and you're going to start with, you have a list of names and the number of times you're going to pass it for this particular game. So they have a list of names as the first parameter, and they're going to pass it 7 times on each turn. So this first loop puts everyone in the queue. So for every name on the list, it in-queues that. So now you're going to have everyone in the queue represented. Now, while the queue has a person in the list, what it's going to do to simulate is for the range from 1 to n, it's going to dequeue a person and then in-queue them. So it's basically moving around everyone in the queue. So if n were 3, it would dequeue Brad, Kent, and Jane, and then and it would also put them on the other end. So it's moving people through the list. So it's after it's dequeued 3 people, Susan will be the person on the far right. So once this loop is done n times, it dequeues Susan, and she's the one removed forever from the queue. So she's being removed from the circle. And so then it goes up and says, well, we're not done because there's more than one person. So it's going to go through the same process again. So the simulation is just these 4 lines of code here, including the blank line, simulates the entire hot potato game. Of course, there's some setup. You got to put everyone in the queue in the first place. And when you're all done, you dequeue the last person, and she's the winner, or the last person out, however you want to do it. So it just returns that. So when you run it, it says Susan is the winner of the game. So a pretty simple lab simulation. Now the next thing we're going to simulate is computer lab printing. And the reason they say you might do this is it's expensive to invest in buying a lot of stuff and try it out, and you find out you didn't buy enough to actually solve your problem, or you didn't set it up the right way to solve your problem. So it may be less expensive to simulate some kind of system prior to investing in building it. This is true of a lot of cases. Anytime someone builds an airplane or a car design, they will simulate it, and they'll simulate a lot of the different systems in these two things before they actually build it. So they can actually answer a lot of questions about its performance, even the cost of doing it, when will it break down, how it behaves in a crash. There's a lot of things they can simulate now. When they build a bridge, they will use a mathematical model and put it on a computer that simulates the loads on the bridge for all the parts of the bridge, so they can make sure the bridge will support a load or survive in an earthquake. Anytime you build a spacecraft or a rocket, it's going to go places you can't even fix it necessarily. So they always simulate a lot of aspects of spacecraft and rockets before they actually build it. Even when you're building a network, there's a whole group that's working on the next network design. So how will we change the internet, for example, to behave better? Or how are we going to change how wireless systems like cell phones work better with each other? So rather than actually building a network and spending all that money, there's actually software that will simulate a network, and you can change aspects of how it works and then simulate it and find out its characteristics. So you can save a lot of money by doing that. One of the most common simulations you might use is a simulator where you interact with a simulator. So you have a real, quote, real world simulation of some way, and you interact with it. And the most common experience you may have had for this is when you play games. When you play a lot of shooter games or action games on a computer, you're actually involved in a simulation. So the example in the book shows how to simulate a bunch of computers printing in a lab environment where we have several printers, and we want to ask the question, well, what's the maximum and average wait times for getting a printout prior to buying the printers? So we have a lab that has a certain number of students, and we know they print on a certain statistical way they print behavior. So we want to see what's the maximum wait time, for example. Now this type of simulation is actually going to simulate time. So the idea there is you have a main loop that simulates 1 second each time it goes through the loop. And that's how you simulate time. Now of course the computer can simulate much faster than in real time. So the loop may go through 1 billion iterations in a second. So you can simulate 1 billion seconds in 1 second. And that's one of the advantages also of simulation, is if it's a simple simulation, you can simulate before things happen. In fact, this is how the weatherman does things. There's some very, very expensive computers, and they have a model of the weather, and they input what is the current weather, and it simulates what it's going to happen. And they have it now where they can simulate up to 10 days in advance and report it on the weather. Of course, a lot of the nature of simulating very complex systems in the world is it's only an approximation. So they're actually approximating the weather, and that's why the more time they get out, the less accurate the prediction is. It's also why even for predicting rain, they give you chances of rain, because they can't simulate all the chaos that's actually exists in the real system. And they also can't actually simulate it in the amount of precision of the real world. Now also, when you study the code for simulating the lab, you're going to see some more uses of object-oriented programming. So they have a printer class that represents each printer in the simulation. So they define methods that will interact with the other classes. They've added a task class, which represents when a student wants to print something and adds it to the task of printing something, it'll represent that task. So the task might be printing a certain number of pages, or a print job that takes a certain amount of time. And then they just add 2 more functions to help run the simulation. One that has the main loop, and so we can look at that. So let's look at the code for this. There's a little diagram first. Well, there's this description, so how they're going to do it. So they're going to use a queue for the print task. So they're going to create a queue of the print task. Each task will be given a timestamp upon its arrival. So in the simulation, the timestamp will tell when it was first put in the queue. The queue is empty to start. Now for each second of the simulation, they say, does a new print task get created? If so, add it to the queue with the current second as the timestamp. If the printer is not busy, and if a task is waiting, so this is all in this loop for each second. So if a printer is not busy and there's a task waiting, they're going to have to print it. So they remove the task from the queue, assign it to a printer, subtract the timestamp from the current second to compute the waiting time for that task. Then they append the waiting time for that task to the list for later processing. Then based on the number of pages in the print task that's been simulated, they're going to figure out how much time it will be required to print. Okay, and then these are all things happening that second. So in the next second, still in the second, if the printer now does 1 second of printing, so they're going to ask the printer to actually do a second of printing, and it subtracts 1 second from the time required for the printing task it's working on. If the task has been completed by the printer is no longer busy, so the printer is going to change its state. So after the simulation is complete, we compute the average waiting time from the list of waiting times generated. Please subscribe to my YouTube channel. You'll see an icon in the lower right corner you can do that with. Okay, well now we're going to cover what a deck is. It looks like DQ, but it's actually pronounced deck. So deck, also known as a double-ended queue, is an ordered collection of items similar to a queue, but it has 2 ends, a front and a rear, and the items remain positioned as you put them, but you can put them on the front or put them on the rear, or remove them from the front or remove them from the rear. So basically these are the operations: add to rear, remove from rear, add to front, remove from front. And so there's the notion of the rear and the front. And so let's look at our abstract data type for this. So the abstract data type defines a constructor called a deck. It has an add front method, an add rear method, which just take an item. Remove front, which removes the item from the queue. and returns the item. So it's kind of like pop, but removes from the front, and remove rear removes the item from the rear and returns it to you. Is empty asks if the deck is empty, and size returns how many items are in the deck. Notice you can't index and get something in the middle of the deck. It's like a queue. It only allows you to work on in terms of both ends. So here's some test operations. Create a deck and then check if it's empty. We're going to use a list to represent a deck inside of Python, and so that would return true if it's empty. Add the number 4 to the rear, so that goes in the deck. Add rear dog, so that goes onto the left side. So the left side of the list is going to be our rear. Add front cat, that's going to append it to the end of the list, so that goes onto the right side. So the front is this side and the rear is this side, looking at a list. Add front true, get the size, that it returns 4. Test if it's empty, it returns false. Add rear a float point, it adds it to the rear, which is the left side. Remove rear is going to return 8.4. This is what we just added to the rear. Remove front is going to return true, and that is the last thing we added to the front was true. So notice after you remove rear, it removes the 8.4 from the deck, and when you remove front, it removes true from the deck. Here's an implementation. You'll find this in the Python's library that we've linked to from the playlist section, which has all the code for that we're using from the book. But you can also just copy and paste this and put it into a file and use it. Now in the book they have this nice thing that will step through using it. If you haven't used these are built in the interactive book, so you can step through each step. And let me reduce this a little bit, and you'll see that as you step through, it shows you what the deck's pointing. So it's giving you, here's the class for the deck, and as you go forward, and so it's stepping into the deck, and here we're going to add to rear, and you see it happening here, and once it happens you'll see it's added 4 to the list. So you can step through this. There's 45 steps, so that's kind of interesting to do. Let's go to the next part. Oh, and just a note that the front, because we're using a list, when you add, it's removing items from the front is O of 1. What adding and removing from the rear, since it's at the beginning of the list, is O of n. So we're going to use this and make a palindrome checker. So a palindrome is a string that reads the same forward or backward, like radar or toot. So if you read it forward or backwards, it's still radar. So the way we're going to do this is we add the word to a deck, so it ends up, and then we're going to pull from the rear and from the front, and they should match until the deck is empty or there's only one character left. So if there's one character left or the deck is empty and we haven't found any mismatches, we have a palindrome. So the code's pretty simple. A palindrome checker, you pass a string, you create a new queue, call it the char queue. If there's a char in string, you add it to the rear. So this is going to loop through all the characters in the string and add them all to the deck. There's a flag still equal, so we're going to check that to stop the loop. So while the size of the deck is greater than or equal to 1, so as long as there's 2 or more and still equals true, we're going to remove from the rear and the front and rear, check if they're not equal. If they're not equal, we set still equal to false, which would cause the loop to end early. When the loop ends, we just return the flag still equal, and that's it. I've put this into my code. I modified the test code a little bit to print out what it's checking. So I'll show you that running. So this is all the same code, except here I print a string. Let me make this a little wider here. So what I did is I just copied this call that we're doing to check if it's true or false, and I put that into a string. So because it's using double quotes, I put it in a string using single quotes and then little arrow. So when you run this, I'm using a program called TextMate, which is very nice for running simple Python. You can see it says, well, this call returned false and this call returned true. So radar is a palindrome. That's basically it. In the next video, we'll deal with list. Please subscribe to my YouTube channel. You'll see an icon in the lower right corner you can do that with. So Python has a pretty good list. It has an underlying list that they've implemented for us, and it's very powerful. It is powerful for all the most common operations you'd want to do. But we're going to look at how would you implement your own list. So in general, we're going to be implementing an unordered, basically, which means it's unsorted list. So the qualities of an unordered list, it's a collection of items. And like all the linear structures, each item holds a relative position relative to the other items. The list has a first item, a second item, and so on. And you can refer to the first and the last item of a list. Potential operations you would have on a list would be creating a new list, of course. Add an item where you pass a piece of data or a reference to an object and it adds it to the list. Remove an item where you pass it a reference to an object you want to remove. You could also have a remove that takes an index number. So we're looking at all the possible operations you could do. You could search for a piece of data. So you give it an object that has some data and it finds the same object and data on the list. You can check if the list is empty. You can get the length of the list, how many items are on the list. You can append an item to the end of the list, which is to the far right, looking at it from left to right. You can get an item by index. Oh, actually, this is to search for an item. So this searches for item and returns its index. So it's like search, where this returns true or false. This one returns the location on the list. There's pop, which will remove something from the last item. So that's the opposite of append. That adds to the last, and this would pop it. So just using append and pop, you would have a stack. There's pop from a certain position. So this is an integer position of what element you want to remove. You can do a set where you give it a position, and this actually should be a item that you want to change. So this would look up the element at this position and change it to this item. So it's basically assigning to a position in the list. And then get would return the item that is at this position. Now let's back up and look a little bit about talking about pointers. So when we have a variable in Python or almost any language that points to an object, it's actually a name, and it basically points to a place in real memory. So I have a little diagram here of real memory. We have memory addresses, and I've made these memory addresses in normal computers. The memory address is by byte boundary. So if you had 4 bytes per int, for example, each of these boxes would represent one int. So if I pointed to this location 104, I could store one integer in that box. And that's kind of what memory looks like. So if I have a variable count equals 203 and I do that statement in Python, first it allocates a name inside Python called count, and then it finds a place in memory that's free, and then it's going to store this location in that memory. So after we've done that, the now count will be, the name will have an actual address number associated with it, and that address number we call an object reference because it points to where that object really is in memory. And so this would point to that integer in memory. So this is the same with arrays, and it's very similar to list in Python, that whenever you assign a variable, you're actually going to point to somewhere in real memory. So we can always think of a variable name and then have this pointer that points to memory. Now we don't really need to know these numbers. They're interesting if you get down to the machine level and you're debugging at the machine level. But for most programming, you just need to know that points to a place in memory. In most languages, you can get a number called a reference or a hash or a ID. It's called an ID in Python, and it gives you a unique number that which represents the actual memory location. So that's the abstract point of view. We just think of count pointing to a piece of data in memory. So here's a class. So we're going to show you how a class looks like in memory. So when you have a more complex data that's got more than one element, you basically create a class and you create objects of that class. So here's a point class. So I have class point. I have something to initialize two instance variables, to x and y. And so when I say p1 equals point and give it two numbers, it creates a memory. It initializes it to those two numbers. So this first slot would be the self.x slot. Well, self actually refers to the whole thing, and the self.x would reference just the first slot, and self.y would reference the second slot. And then p1, which is now assigned to refer to that object, basically points to where the object is in memory. So we can also think of, especially since objects are used everywhere in Python, every variable we have will point to an object of a type in memory, and it will have a certain number of memory locations allocated toward it. Now let's look at interesting structure. We're going to look at what something looks like in memory. So let's consider this structure. Now what this is, I build a list here on the inner. So this is actually a tuple. This is actually a list. The first element is C, and the second element is none. So you notice there's a pair. And then this list is the second element of this other list, which starts with B and then this list. And then this third list starts with A, and it has to the right this inner structure. So each one of these things is an object, but the list are more complex objects. So let's look at what it looks like. So I'm just going to copy this expression, and I'm going to go to the Python and visualizer, and I already have it open, and I'm going to paste that in, and then I'm going to visualize it, and then we're going to step forward, and we'll see we have something very interesting. This is what's called a linked list structure, and what you'll see is A points to the first list item. Each list item this thing is called a node, and so you have a piece of data, and then you have a pointer to another node which has a piece of data, and a pointer to another node which has a piece of data, and lastly it doesn't have any more, so it has none. So this is actually how you store a list item. So I just wanted to show you how simple a structure it is. You can write it on one line. Now we're going to work with a structure like this, but we want to be able to insert into it and take things out of it and add things to either end. So we're going to make a class out of it, so it's going to be more complex than just trying to do it in one line. But this is the basic idea. This is about as simple as you could write what's called a linked list. It's called links because your first variable just points to the front of it here, or it's usually called the head. And then as you add items, you add them to the head and you push them down like this. And if you want to see what's in the list, you have to follow the link. So you follow a link to this pair, and then you follow the second piece of data to this pair, and so on. So you follow these links, which are usually called next, or in the linked list structure. And then when you finally get to a link that's not set to anything, it's set to none, you know you've reached the end of the list. So here's that structure. Let's look at something, a simple class that would store these nodes, which are the individual pieces of data and links. So here's a class called node. Here's an initializer that takes a piece of data we want to store, and it creates a brand new node and sets the data to point to that data, and it sets a link called next to point to none initially. And so we can create a blank node and store that in first, And then we can say first.next. That's going to go into that first object and look at the next value, and it's going to point that to another node. And the data for that's going to be B. And then lastly, we're going to take first, which we're going to take next, which is going to point to the first node. And in that node, we're going to go next, which will be the link from the second node B, and we're going to set that to C. So we're going to look at what this looks like in the initializer, and you're going to see it looks just like our previous example. So I'm going to go Edit. I'm going to replace this code with our new code, and then I'm going to step through it. Let's see, visualize it, and go forward. Now, one thing about the visualizer, it does everything. So it's going to step into every time we create a new node. So we're going to follow it into this new node. But you'll see right away there's just it's created a node, and it has just one attribute, which is the method available. And we're going to go forward. Okay, and now it's assigned an object, which is known as self. And so the self points to just an empty instance right now. And then we're going to assign data, so you can see now it's changed from an empty object to self pointing to an instance variable that has the data A. And then we go forward and it's about to return. So now self points to the full object instance, which has the data, and the next pointing to nothing. And then we'll go forward. It's going to go back to here, and we're going to make node B. So I'm just going to step through that until it returns. And after that's returned, you notice that first here now points to this node, but next has now been set to point to this new B node. And then we'll step through till this is done. And you'll see we have the same structure. We have first, a variable on the outside, points to the first node of this list. The next node's next value points to the next node in the list, and that value points to the next. And so we have a linked list. Now why this is important is because this is basically a very efficient way to build a list in memory. It's very flexible. You can insert things in the middle, we're going to see. You can delete things from the middle. You can add to either end. And so we're going to examine this whole structure because this is a very important structure in computer science. Now we get to the more complex stuff. Now you especially want to pay attention to how these work. We have an assignment for you which works with doubly linked list. So you have to pay attention to the techniques used to create these operations. So they want to remove something from the list. So let's look at, this is always useful if you draw a diagram of what things are like on the list before you remove something and after you remove something. And why that's important, you can see before we start, the head points to this list, and we're actually removing this item here. So this is what the list will have to look like when we're all done. This item will be gone, and you'll see this link here no longer points to the gone item. It has to point across to the item that the old item used to point to. So that kind of gives you a clue the operations you have to do. So basically you want to change this next to point to this item that's the one that the item you're removing is next used to point to. So you're basically going to be assigning this next to what this next was. And that's how you actually remove something. So we're going to have a loop that's going to look for the item we're going to remove. So it's advancing current until it finds the item we want to remove. So once you have a pointer to current, now we can actually look at doing that. But we have one problem. We have to actually change this node back here, and once we advance to current here, we no longer have any reference to the previous node. So you're going to quickly find out that when you write this code, where you have to modify something in the previous link because you're removing the one that you found, you have to remember this last one. So we're going to add a new variable. So we're going to add a previous. So we're going to have our code keep track of not just the current, which will be the code we've already looked at, but the previous one we looked at. So when we find current, we're going to have this previous, and then we can refer to previous.next and set it equal to current.next, and that would effectively erase this node. And that's what we do here. So this is just searching for data matching item. So this is the same as the search. But once it finds it, instead of returning true, it sets previous. It sets the next value of previous to the current. Oh, I should have said dot get next. And now that's gotten too big. Let me decrease the font a little bit. Okay. And and it's a long line. It should really be indented. So you can see that's caused some problems here. So I'm going to see if I can fix that up. Yeah. Some of these on my slides are problems because I use previous.next instead of setNext, which is a lot shorter code, so you can access things. So this gets the next value of current and then sets next for previous to that. And then after it's done that, it can just return it's all done. It's deleted the item. Now, then it gets, here's how it remembers previous. So before it gets the next, in other words, before it changes current, it remembers current into the previous variable, and then it gets current pointing to the next node. So when it comes back on the loop here, previous will always point to the previous node to what current is. Okay, here's remove. There is a problem. What if this is the first item in the list? Suppose you match the first item in the list. Well, let's look at the problem here. What happens if it's the first item in the list you're deleting? Current will point to head, and head will point to that item that we're going to delete. So current is okay, but previous is set to none. So while current is not equal to none, it says, okay, the current isn't none, it points to something. So you get the data and it matches what we want to delete. So then it says, oh, we don't have, let's just fix this to the other code. I'm just going to refer to next directly. That's what I had originally. And then it's not a method. Okay, there we go. So it sets the next of previous to current, but there's a problem. This will actually give you an error because previous is none. It doesn't point to anything. There is no previous to the first item. So this is the special cases I was talking about. And so when you have that, when previous doesn't point to anything, in this case we need to change the self.head to point to the next node. So previous is like the self.head is what we need to change. So we have to put a special case in. We have to actually test for it. So when we match our data, we check is previous equal to none. If it is, we set the head of the whole list to current. Else we do what we were doing before. And let me fix that up as well. Next is equal to current. There we go. And that's it. All right. So now let's so special cases, and this is especially going to be true of the homework. Special cases often arise in algorithms when you work with a list of things or structures where you're at the beginning or the end, or there's nothing in the structure. So those are always special cases. There's two things you should do. You should always think about the special case if your code will work in that case, and then you also should test your code if it actually works for those cases. So for example, when I work on tests that test your code, I always will test the case where there's no list. There's maybe only one item in the list. Sometimes that's a special case. And I'll also check if you're deleting or doing something with the beginning or the end of a sequence as a special case. Okay, the last part is an ordered list. Now the only difference between an unordered and an ordered is whether it's sorted or not. That's when you read this, you're not clear exactly what is ordered and unordered. But it has to do with whether the items in the list are in a numerical special order, either numerically or alphabetically. And so we can use almost everything we've done alright will work fine, because once you put things in the list, if it's sorted, deleting them out of the list or counting them will not change the order, because remember, the list retains the order once you put it in. So it's inserting into the list that we really have to be concerned with getting in the right order. And the idea is here is we have a list and we want to insert a number like 11. We basically just have to find where does it go. We search. You see the list is already all sorted from smallest to largest. So you can see it would go after the 7 and before the 15, so it gets inserted here. So the trick is we want to search for this node that is the one we want to insert it before, but we also want to reference the one before it. So these nodes it goes between, we have to change this link, and we're going to have to change the link of the node we're inserting the point here. So we need a reference to both of these. So first thing is we're going to have a search which finds previous and current. So this will be exactly the same as if we were deleting that node. We're finding current, but we're going to be inserting something in front of it. So it finds the first node that is bigger than 11. So we're inserting 11. The 15 would be the first node that's bigger. So we want to stop where current points to the first node that meets that condition. Now once we've done that, we're going to erase this next, for previous next will be erased. And then the new node's next will be set to what it used to point to. And that does it. That will insert the new node. So here's the code, and it's a bit longer. So there's also a special case here. So let's see if we can look at the code here. So I called it add order in order because I actually added it to the original unordered list class to test it rather than copying the whole class and leaving everything else the same. So I can either insert into a list sorted, or I can insert by just doing add. There's a caveat about doing that. I just did it because it was easy. But the problem is if someone does the other add to add a bunch of items and they're not in sorted order, the list is, quote, broken in terms it's not an ordered list. Once it's not an ordered list, this method will not work. It assumes that the list has previously been ordered. Okay, so we have, this looks very much like we're going to delete something, except here we create a brand new node with our item. So we're going to insert that later. The author actually does this after the loop finishes. You can do it either place. Then we have a special variable to indicate when we want to stop. And this actually simplifies the code a bit. So while current is not equal to none, we've done that before, and not stop. So we have two conditions that we might stop on. Turns out one of them is we found the item, which is the not stop, and one of them is we reached the end of the list. So if the current data is greater than item, that's the condition we're looking for, we set stop equal to true. Else, we set previous to current to remember our previous value, and then we set current to the next value. Okay, now when this loop is all done, we get to here. We've actually arrived here in two different cases. One is there was nothing on the list. So we're actually inserting on an empty list, and in which case previous will be none. And then the other case is normal, where we found the thing that has, where previous actually points to something. So we found something on the list. So, and it turns out, okay, so if previous is none, we either have one item on the list or no items on the list. And it turns out this code works in either case. We set the new node to whatever self head is. Self head actually points to something. That means that we were inserting before the first item. If self head is none, we're actually inserting into an empty list. But either way, this will set the right pointer for the new node. And then finally, we set the head to point to the new node. So that inserts into the first position. So in this case, in the normal case, current is pointing to after we want to insert it. So we set the new node to point to current, being the next node it's going to be inserted before. And then the previous node, we set its next to point to the new node. So that will create the links to insert this new thing in. Now the big O of list, every method on the list that does traversal has to go from 0 to n steps. So automatically all those methods are basically O of n. And here's a list of all of them, getting the length. Now there is a shortcut in the length. You can add an extra instance variable to the unordered list object that keeps track of the length. And every time you add something, you increment it by 1. And every time you remove something, you subtract 1. And that adds a little bit of cost to inserting and taking out things in the list. But it gives you the advantage that every time you ask for the length, you don't have to traverse the list. So length would go from O of n to O of 1, a constant time. So that's an improvement you can do on this structure. We have remove, append, pop from a certain index because you have to find the index. Search, index are both search operations. Insert, you have to find that item. Pop from the end of the list, you have to go all the way to the end of the list. And pop from an arbitrary place in the middle is also O of n as long as I is random between 0 and n. And so that's it. One more thing. This has to do with your homework assignment. So this is the picture of a doubly linked list. It's just like a linked list, but you can traverse it from either the rear, because it has links that always point to the previous value, and from the front. You can see one advantage is that when you traverse coming from the front, you don't have to remember the previous value. You have a pointer to it in the node you find. So that's an advantage. But if you insert or delete, you have to change all these nodes, twice as many nodes to put something in or remove it. So here's the actual definition of the node for a doubly linked list. So we have a next, and we also have a previous pointer. And so here's a picture of it. The first item's previous points to none, and the last item's previous points to none. There's one more special case when you consider this. There's if you only have one item in the list, when you have no items on the list, and whether you're doing something at the beginning or the end of the list. So those are several different cases you have to consider that you test for all those. But again, I'll do them. You have to test for if you have an empty list. Does your operation work? Test if your operation is affecting the first item in the list, or if it's affecting the last item in the list. Does your operation work? And then finally, test if your list works when there's only one item on the list. And that turns out to be a special case. So good luck with the homework, and we'll see you later.